Okay, so we're ready to apply backward induction to make this one big problem very big. So I'll take you through this. So here's what we're going to do. We're going to define this thing called, it has various names. It's going to be called a value function. So this is going to be the value of the problem starting in period t, capital T, when you face state x. And this is just going to be our terminal value. That's just the value at the end. And we made that up. We made up that matrix, that terminal value matrix, RF. That's our last state. Okay, so we're now going to consider the, so again, we've broken this into a bunch of little periods, and this is the last period when we're choosing ut minus 1, and this is just fixed. Okay, so we're going to let the time period be t minus 1 and suppose that the state is xt minus 1. Now, the key thing is we're going to imagine that the state is just given. So what's the problem that second to that last period? Okay, so what the person, the decision maker wants to do, he wants to minimize. Well, this is what he's going to get this period. We just wrote that down. The state this period, plus this quadratic term in his control, plus beta times the expectation. And we can again, if there's no w, we can just ignore the expectation, times jt of next period state. But what next period state is going to be something that he's going to influence. See, the key thing is jt, the value function takes the state as given. But from the point of view of the previous period, your choice of u is going to influence what that state is. And how's it going to influence it? Well, with our transition law. So stare at that. Almost everything is in this equation. So we're going to define a recursion. So notice where this is. This is a minimization problem. And when we're choosing u, we have two things to consider. Its effect on the loss today and the effect on the discounted loss tomorrow through its influence on next period state. That's a mouthful, but that's what this is saying. U is entering here and it's entering here. So Bellman's idea was, let's define this function, jt minus 1. It's going to be a value function, and it's going to be a function of the state at time t minus 1, and it's going to be the optimal. It's going to be the best possible j. It's the optimal value function, which means it's the value of this problem up here. So we're going to minimize over u these two things, and we're just going to define a function jt minus 1. And this has when it's a loss function, it's called the loss to go. You'll find that in the literature, or it's a value function. So it's the period t minus 1 value function. So it satisfies, this is an equation that for the linear quadratic case is going to be really easy to analyze. Okay, good. Okay, very good. So now we're going to just go back. We've kind of done our first step of backward induction. We're just going to do it again. So this little observation is key towards staring at. We're just going to do for period t minus 2 what we did for t. And this is just all repetition. Xt minus 1 is equal to this. Looks just like what we did before. So now our problem, looks just like our problem, just with a shift of the date. And we're going to define a value function here, jt minus 2. It's going to be defined just as before. And instead of t here, we're going to have t minus 1. Now, we constructed this in the previous step. So now what we have is we have this key equation. This is called a Bellman equation in honor of Richard Bellman. We're going to define a sequence of value functions where we're given the terminal value function, we make it up, and then we're going to work backwards, this one, this one, this one, this one, by solving this sequence of equations. Okay, so if we had these value functions, if we knew what they were, we'd be in great shape because we can figure out what the optimal control is. So our next step is to figure out what the optimal control is and then do a little staring, and we'll quickly see how to figure out what the value functions look like. So this is a key line. For linear quadratic problems, it turns out that these value functions have a very simple form. Look at this. JTX is going to turn out to be a quadratic form itself in this state. We've minimized out the controls, and a constant. And PT is going to be an n by n matrix, and DT is going to be a constant. And they're very easy to compute. So now you'll notice the following. This conforms with this. The way we made this up is we started with a terminal value function that was quadratic. We made that up. And then all we have to verify is if we do one step, do we still get a quadratic term, perhaps plus a constant? The answer is going to be yes. So if we do this, we can just do one step. Here's the key line. And we're going to use some matrix calculus. There's very simple formulas for, you can find them in Wikipedia, or I can give them to you, for differentiating linear and quadratic forms. So our problem is, here's our Bellman equation. We now have this quadratic form here. Here's our problem. We want to minimize this with respect to u. If we take the first order conditions and rearrange, we get the following expression for the optimal u, which is beautiful. And I don't want you, I'm not necessarily going to give you tests on these formulas. I just want you to know they exist because they're very powerful to use. So notice the u is it involves q, beta, b. It involves next period's value function. But at time t, we know that. Time t minus 1, we know it because we've computed it. There it is. So if you stare at all of this, the control u is a linear function. All of this is just a bunch of matrices. It's a linear function of the state. Your optimal control is a linear function of the state. And if you plug that back in, you'll find, if you just plug this control in here, that's just linear algebra, and I'm not going to force you to do that. I don't enjoy doing it myself, but you can trust me. If you do that linear algebra and substitute back in, what you're going to find is this value function is now going to be a new quadratic form. It's going to be a quadratic form where P is going to satisfy this. So this P is this thing over here. It's a big, long equation. It actually has a famous name. It's called the Riccati equation. You may have heard of that. This is called a Riccati difference equation. So this is a key equation because the way we solve this problem, we just summarize this. So notice this equation. If you know beta, the discount factor, A, B, Q, and R, and I give you a terminal P, you can just iterate backwards on this equation and get the optimum value function for every date And once you know the optimal value function, you can get out the optimal decision for every date. So you're done. So these two equations are what come out of linear quadratic dynamic programming. And then there's a very easy formula for the D's, and the D's only come in if the C's are not zero. If there's no randomness, there's no D's. And notice the following. There's something really interesting. This is an important principle. Some famous economists wrote a book about this. Actually, Modigliani, Muth, Simon, and Holt. And what they notice is if you look at the formula for U, you don't see C. Look at the formula for P, you don't see C. It's remarkable. So the noise statistics, the volatilities, don't affect the decision rule, and they don't affect the P in the value function. They only affect the D. Okay, so here's what we have. To compute the P's, we just iterate backwards on this equation. That's called the Riccati equation. It's as easy as pie to do. And then once you know the P's, you pre-compute the P's. Once you know the P's, you can get all the decision rules from right here. Those are linear optimal controls. And that's it. So now, notice what we have. If we've solved the problem, the UTs are a perhaps time-varying function, but linear function of the x's. We substitute this into our state equation and rearrange. We get the law of motion for x that's optimally controlled. It's just a minus bft xt plus these noises. That's it. So that's how we use dynamic programming. We have this key equation right here. That's our key equation. So we need this equation and this equation here. So what's the takeaway from this? If I give you a problem that has a finite horizon, and I give you an A, a B, a C, a Q, and an R, you can just apply these formulas, and a beta. You can apply these formulas and tell me how to, and compute the optimum decision rule. It's very powerful. And all we're using is a linear algebra and backward induction. So let's go to this example that we want to talk about. So we're going to use this. We're going to use this logic to talk about several models. Remember, one of the things we encountered in the first lecture was the question, well, how should you finance a war? Should you tax or should you borrow? And more generally, if you're going to borrow, how should you borrow? Should you borrow short-term or long-term? What should you do? And famous economist, he's now at Harvard, Robert Barro, has thought hard about this, and he sketched some models that we can actually improve on his models a little bit by formulating them as dynamic programming problems, because we can actually clarify exactly what he had in mind. So we're going to do that in various steps. So to do it, we'll visit two other famous economists, well, several of them, Keynes and Milton Friedman. So Milton Friedman was interested in studying the consumption function because the early Keynesian consumption function didn't work very well. In the sense that it made predictions that the data after the World War II contradicted rather severely, and Friedman wanted to understand why. So what he did is he wrote down. He was influenced by Irving Fisher, who had started on this line 50 years earlier. He was going to write down a theory of optimal consumption behavior. So, here was his model. He's going to have a consumer, typical consumer. And Milton Friedman actually applied this to consumers with different situations. Actually studied black people and white people, rich people and poor people. But every consumer in sight is going to want to maximize, or is going to want to minimize this loss function. And CT minus C bar. C bar is bliss consumption, and it's a really big number. So what the consumer, this specification makes the marginal utility of consumption linear in consumption. The guy likes more consumption to compute the marginal utility of this. And then we impose this terminal condition, and this terminal condition is going to force the person to end the period with close to zero assets, to end his life. When we talk about Barro, we're going to set t equal to plus infinity. We're going to drive t to infinity. And let me tell you why we're going to do that. It's for a ruthless practical reason. Look at this equation right here. And look at this decision rule UT. This equation basically says for every date, there's a different decision rule. It's linear, but it depends on t. Wouldn't it be nice if it didn't depend on t? If it was just, if I could erase this t. If I could erase this t. Well, I can only erase this t if I can erase this t. How could I erase this t? Well, that has to satisfy this equation for all t. Well, wouldn't it be great if the p's actually turned out all to be the same? Well, how could that ever be? Well, it could be true as if t were, capital T, were very far into the future. And I've iterated on this equation a really, really long time, and these p's converge. So if these p's converged, then the f's will converge. And under some very general conditions, they will. So if we drive capital T toward infinity, we can erase the t's from this equation and this equation. And actually, Milton Friedman used that, and Barro used it. Okay. So if we drive capital T to infinity in the proper way, some nice things are going to happen. Okay. So these notes that on QuantEcon that I'm drawing this from discuss this issue in enough detail, I think. Okay, so here's our criterion function, and here's the law of motion that we wrote with Milton Friedman, that we wrote with our model. The consumer has the ability, the consumer gets some non-financial income, has the ability to buy or sell an asset, a risk-free asset that bears a constant risk-free rate of return of R, gross rate of return of 1 plus R. Okay. So what are we going to do? So let's take the really simple case we analyzed before. It would be easy to generalize this and fun and important. We're just going to have a simple example where your income is equal to so think of this as your labor income. So you get some constant mean, but you're in a business where that's risky, so your income fluctuates according to this normal distribution. And we know how to map this into our linear state space system. We did that. So we have an A, a B, and a C. And then with our criterion function that we've given, it's very easy to compute what R, Q, and RF are. They're very simple. So, I don't know, we coded this up. And so let's see what you get out of this. You get a telltale sign. You get something telltale. So we've made this up. So here's our non-financial income. So this is actually generated. How did we solve this? Well, we iterated on those equations, those Riccati equations. We computed PT minus 1 as that big long function of PT and A and B and all that stuff. And then we computed UT, which is equal to CT minus C bar, is equal to minus that number FTXT, which computed that. Actually, we set this up so that this person is going to, capital T is equal to 45. Set this up like this. So the green line here is his non-financial income. It's fluctuating all over the place. And we set its mean to be 1. So you see its mean is 1. And we started him off with 0 assets, I believe. You can check that. Okay. So the striking thing about this is this black line is his consumption. And the green line is his non-financial income. So what the person is doing is he's using saving and dissaving at the risk-free rate of R. Well, I have to tell you what, this is Milton Friedman and Robert Hall and Robert Barro's assumption. We set 1 plus R to equal the reciprocal of the discount factor. That's important. That shaped this. So it's a pretty high interest rate relative to your discount factor. And a lot of people think that's quite a good approximation to what's in the data. So what this person does, you can see what this person does is the blue line here is his assets. And early on, the person in this sample builds up his assets. He saves. He starts at 0. He saves. And then he's got some bad luck in here. Look what happens in here. He has some bad luck. And he runs his assets down. Some good luck in here, runs his assets up. And we've rigged this so he actually wants to end this with 0 assets. So that's what happens here. And you could read this. There's some alternative examples here. So there's an extension here that I want to show you. This is very easy to do. This certainty equivalence principle tells you C does not influence P, any of the sequence, and it does not influence FT. That's important. That's what that's saying in there. Okay. Okay, well, actually, if you're interested in programming, there's some code, and I'm not going to make you do that, although you should know it's available. Turns out to be really easy code to write. Okay, so we changed this in the following way. We made the following. We rigged this with the following. This is a painful thing to admit at my age and my place in the life cycle, but what happens is young people, your income is just not constant IID. It rises with age and experience, and then it declines later in your life cycle. So we've rigged, you could see it's very easy to change the A matrix to capture a stochastic, a random income process that looks like this, just so that green one. So we've done that, and then recomputed the optimum, and then again, the person smooths his consumption. And what does he do? Look at this. Early on in his life, or her life, so they know they know their income process is going to, they can't predict it perfectly, but they know that there's going to be this hump shape. This is a famous hump shape in the income process. So what does the person do in anticipation of that, according to the Friedman model? Well, early on, the person borrows. So runs down his assets, starts at zero. So it's borrowing early on. So young people are borrowing, and then later builds up assets in order to compensate for the declining income. So so then this can easily be souped up to have a model of retirement. So we change the person's income to look like this. Oh man, this scares me even more, given where I am. We changed it so that after 41 years in the labor force, the guy is forced to retire and gets zero non-financial income. So his income process now looks like this. And you could see it's very easy to make up an A and a B. We put time steps matrices on these to model this. So what does this guy do? Now this starts looking really good. What the person does is early on, again, it borrows because he knows his income is going to go up. But then later in his life, he builds up assets. And why does he build up those assets? Because he realizes that this zero income is coming, and then he's going to have to live off his savings. So that's what's in here. Okay. So this was all these things were all just computed by taking an A, a B, a C, an R, and a Q appropriately to capture the income processes that we wanted and the preferences that we wanted, and then we computed what the optimal thing was to do. So this is a compact and very efficient way to actually go beyond what even Milton Friedman did. So what I want to do now is I'm going to go to another lecture. I'm going to show you something it's going to turn out to be really useful for us. Okay, so there's this other lecture later, and what is this called? This is called the Permanent Income Model 2. It's on page 465, and I just want to point out, something to you. So far we haven't mentioned Barro. So remember what the Friedman problem is. The person cares about this, and we're just going to switch to make this infinity. And then the person has this this choice. Gets this, then gets the interest and the principal on his assets, and then they're just one period assets, and he has this labor income, and this is exogenous in this model. Okay, so this has a number of properties. The key property that came out of this model, and we could make up any income. The striking thing that happens from this model is that you can make up any income process that you want. And no matter what it is, the person's going to want a consumption smooth. It's a drastic consumption smoothing that's using savings to erase, to make consumption look much smoother than income. Okay. So there's this nice word called isomorphic. What that means, morphic means structure. Iso means the same. Typo. Okay, so I'm going to show you this is an insight that Barro had, although he didn't write it this way. He could have. It's clearly the way he thought of it. There's going to be, well, so here's our model that we have. I've just written it in a slightly different way here. It's going to be convenient. I've called this a borrowing plan. You'll see I've defined AT is equal to 1 plus R BT. That's all I've done. Okay, so we saw how we could map a version of this model. So the isomorphism is this. What Barro said is he's going to convert Friedman's on Hall's model of consumption smoothing into a model of tax smoothing. So instead of consumption smoothing, it's going to be tax smoothing. So here's the change. In the Friedman's permanent income model, the LQ permanent income model, the household's going to face an exogenous non-financial income, and it's going to choose to smooth consumption. So this is what it chooses, and this is what it faces. So here's what Barro's going to do. There's going to be a government, and it's going to face an exogenous sequence of government purchases that it's going to have to finance. So these wars are just going to be exogenous. So there's going to be periods when there's wars, just like I showed you for England, that graph for England. And what the government wants to do, it wants to smooth taxes over time. And the reason it wants to smooth taxes over time is it has the view, and this is Barro's insight, that taxes are distorting and that you can minimize those distortions by having taxes be smooth. So what Barro wants to do is he wants to minimize TT squared, whereas what Friedman wanted to minimize was CT minus C bar squared. So what's Barro going to do? He's going to set government purchases. He might change signs. He's going to set government purchases in his model to non-financial income in Friedman's model. He's going to equate those. And he's going to take total tax collections and he's going to equate those in his model to consumption. And that's exactly what he did. And if you do that, what you'll get is the pictures that we had before. You'll have government expenditures are going to be very unsmooth in response to wars, and tax collections are going to be much smoother. And what, in place of assets, assets in the consumption smoothing model are going to be essentially minus government debt in the Barro model. So what we have here is through the back door, we've told you how Barro's model works, and we've written down a dynamic programming problem that can be used to solve it. And I think what I'm going to do when I find some space here, I just can do it over here. Let's just do a very simple version of Barro's model. We'll even do a non-stochastic version. Here's what the government cares about. I'm going to change the notation a little bit. I'm going to have, the government's going to do is, it's going to have government expenditure. See if this reminds you of anything. It's going to have government expenditures plus the government's going to have to do, this brand new notation that we're going to have. The government's going to have to pay, let's call it, this is new notation, meaning um, not related to what's previous in the lecture. What the government's going to have now is it's going to have to pay B T minus 1 T. And what that is goods that it promised to deliver yesterday, today. And then what it can do is it can tax today. There's a total tax collections. And then there's going to be these arrow prices. Today it's going to promise to pay that tomorrow. And what we're going to assume, so that's an arrow Hicks price. So what the government can do today is that it can raise revenues by taxes. Those are total tax collections, or it can borrow. And how does it borrow? It promises to pay this amount tomorrow. So today, that's today, and that's tomorrow. So it promises to pay that many goods tomorrow. And how many does it get? It gets that arrow price. And then this says that, well, tomorrow is going to become today tomorrow. So it comes into the period having promised that. And what did Barro assume? He assumed, in terms of our notation from last time, he assumed that this arrow securities price was just equal to beta. So if you promise to deliver $100 tomorrow, you're only going to get beta times $100 today because of that discount factor. And Barro explicitly assumed that this arrow securities price is linked to this discount factor. So this is Barro's model. That's Barro's model. And we can make this fit into our linear quadratic dynamic programming problem very easily. So in Barro's model, the content of this is what Barro assumed that he assumed several things. The only government borrowing is one period. It's risk-free. You might want to change that, but he didn't. And the arrow security price is a particular value, and it does not depend on time. The one period arrow security price, there's no T. Even though there's time there, it's the same one period security price all the time. That's Barro's model. He's a brilliant economist. He really simplified things. Now, what we might want to do, and for various reasons, so Barro's model is going to be very good about some things. It's going to tell us about tax smoothing. It's going to give us sharp predictions about tax smoothing. It's going to be completely silent about should the government borrow long or short. It's going to be completely silent about how should the government respond to different interest rates that it observes, because of this, Barro assumed that the interest rates are always constant. But if we wanted to talk about those things, we might want to generalize the model. And you remember last time, and I think you'll fondly remember this because you've been working on the homework. Last time I gave you a homework where, there were these things. There were one period arrow security prices and 2 period arrow security prices. And there were assets that promised, they had payment streams like this: OTT plus 1, OTT plus 2. So what happens if the government if we want to modify the Barro model to have longer and shorter term debt, and ask what should the government do if it has access to those? And George and I are going to find, when we show you some data, that political authorities in the United States, in our historical events, they were concerned about whether they borrowed short or long, and they had strong views on it. And we might want to talk about a theoretical framework for thinking about that. And to do that, Barro is a good starting point, but we're going to have to add some terms to this along the lines of what we did in the last lecture. It's going to turn out that the linear quadratic dynamic programming problem is going to allow us to do that pretty easily. So if you're willing to like invest a couple hours in trying to digest the structure of this dynamic programming problem and the power of backward induction, I think there'd be some big payoff to it. So I'm just going to go back and I'll conclude, I hope, by showing you this this key equation. We saw various versions where we did backward induction. My little picture that I had, my stupid little picture about this flow that was going in this direction that allowed us to, because the system was moving forward in this way, it allowed us to use backward induction. And it led to these wonderful equations of this very simple form. Simple if you're a computer. Those Riccati equations. Let's see there. Here they are, right here. On page 372, it looks like. So I think where I'd like to conclude now is just to reiterate that these little linear algebra equations allow us to solve some problems that would be hard to solve without them. Before dynamic programming was invented, problems like this were intractable. And now we can solve them and analyze them quite readily. So I think that's where I'd like to stop today.